let's dive into one of the most important, but maybe most overlooked components in all of engineering. We're talking about a part so fundamental that, honestly, our entire modern world would literally grind to a halt without it. It's the unseen engine in pretty much everything that moves. We're talking about bearings.
I mean, just think about it for a second. The wheels on your car, the hard drive spinning in your computer, those gigantic wind turbines, even the super high-speed drills at the dentist's office, they all rely on this one critical piece of tech. So what's this invisible force? Well, it's all about winning the constant, silent battle against nature's biggest obstacle, friction.
So what does a bearing actually do? Well, it boils down to two crucial things. First, it constrains motion. It forces a part to move only in the way you want it to. You know, like a shaft that spins perfectly true without any wobble. Second, and this is the big one, it slashes friction. And friction is the #1 enemy of any machine.
To really appreciate the genius behind the bearing, you first have to understand the problem it was designed to solve. And that problem is friction. It's this universal force that pushes back against every single thing that tries to move. The thing about friction is that it's just incredibly destructive. It's an energy thief, turning useful motion into wasted heat, which causes machines to overheat and eventually fail. At the same time, it's literally grinding down components, causing wear and tear. This is the exact battle that every engineer has to fight, from folks building ancient chariots all the way to today's aerospace designers. So, how did we first start to win this fight? Well, with one of the simplest and oldest solutions out there, the bushing. A bushing is basically just a sleeve. It's a very simple type of plain bearing. You put it between a shaft and its housing, and now, instead of two really important parts grinding away at each other, they just slide smoothly on the bushing surface. The key principle here, the word to remember, is sliding. A simple hinge on a door, that's a perfect everyday example of a bushing. Okay, so this table lays out the fundamental trade-off perfectly. You've got bushings, which are all about sliding motion. Yeah, they have higher friction, but they're fantastic for heavy, static loads. Think massive construction equipment. Bearings, on the other hand, use rolling motion. This creates way less friction, which makes them absolutely ideal for high speeds and dynamic loads, like you'd find in a high-performance electric motor. And that brings us to the game-changing idea that truly powered the Industrial Revolution and, well, everything since. The idea was incredibly simple, but its impact was massive. Why slide when you can roll? NASA actually summed it up perfectly. It just makes intuitive sense, right? The force you need to roll a ball is so much smaller than the force you need to drag it across the surface. By putting little rolling things between two surfaces, you completely change the physics of the situation, and friction just plummets. So let's quickly break down a typical ball bearing. On the very inside, you have the inner race that fits right onto the spinning shaft. On the outside, you've got the outer race, which sits inside the stationary part, the housing. The magic, of course, happens right in between with the rolling elements, in this case, balls. And to make sure they all stay perfectly spaced out and don't bunch up, there's the cage. It's just a really elegant system, all designed for one thing: smooth, low-friction rotation. And because this design is just so incredibly effective, you find rolling element bearings absolutely everywhere. They're in your car's wheels, they're on the Mars Rover, they're in those dental drills that spin at hundreds of thousands of RPM, and they are the absolute backbone of factory robotics and modern aerospace systems. But, what happens when standard just isn't good enough? What about those crazy environments where the temperatures are scorching hot, the speeds are astronomical, and failure is simply not an option? I mean, just try to imagine what's going on inside a running jet engine. You've got unbelievable heat, incredible rotational forces, and you demand absolute perfect reliability. A standard steel bearing? It probably wouldn't last very long. This is where material science really starts to shine. And right here, we see the next big step in the evolution. On one side, you have your traditional steel bearings. They're the workhorse of the industry. They're strong, they're reliable, they're cost-effective. But for those extreme performance applications, we turn to ceramics. Ceramic bearings can handle way higher temperatures, they're much lighter, which allows for insane speeds, and they have even lower friction. The only trade-off? Yeah, they cost a whole lot more. And look, this isn't just some theory. This is the cover of an actual NASA technical report. For decades, organizations like NASA had been researching and perfecting ceramic bearings for the most demanding applications you can possibly imagine, like the main shaft of a gas turbine engine.
It just proves how critical this technology is for pushing the absolute boundaries of what's possible. Okay, so we've gone from sliding to rolling to using advanced materials. What could possibly be next? How do you reduce friction even more than that? Well, the ultimate solution is to just get rid of contact altogether. I mean, if no parts are physically touching each other, then friction, as we know it, basically disappears. And we actually do this with one of the coolest technologies in all of engineering, magnetic levitation. A magnetic bearing is pretty much what it sounds like. It uses these powerful, incredibly precisely controlled electromagnetic fields to make a rotating shaft just float in midair. There is absolutely zero physical contact, which means you get zero wear and you don't need any lubrication. It is the absolute peak of low friction motion. The benefits here are just astounding. With virtually zero friction, they can support the highest rotational speeds of any bearing type, period. And because there's no mechanical wear, their lifespan can be incredibly long. This makes them essential for really sensitive or extreme applications, like the centrifuges that are used for uranium enrichment, or the turbomolecular pumps that create the near-perfect vacuums needed to make computer chips. So from a simple sliding sleeve all the way to levitating magnetic fields, the story of the bearing is really the story of our relentless, brilliant fight against friction. This tiny component let us build our entire modern world and even start exploring others, which kind of leaves us with one final thought. Now that we've all but conquered friction, what's the next great invisible force that we need to overcome? Thanks for watching.